Hello. Now we're going to discuss symmetry in conjunction with even and odd functions. So we can have functions that are even, functions that are odd, and then functions that are neither even nor odd. And they each have their own type of symmetry. First, let's talk about odd functions and their rotational symmetry about the origin. So if you notice, if we look at the origin here, this function, if I picked up this top piece and spun it around at that origin point, it would match exactly. So this picture is a really good example of rotational symmetry about the origin. I do want to note that even though this says odd functions, this picture does not represent a function. It has odd rotational symmetry, but it's not a function. And if I ask you why, most of you should be able to tell me that it's because this function does not pass the vertical line test. If I were to draw a vertical line through this function, it would pass through, or it could pass through at more than one location. So this is not a picture of something that would be considered a function, but it is a nice curve demonstrating, again, rotational symmetry about specifically the origin. Now, functions that are symmetric with respect to the x-axis, meaning we could fold this piece of paper. If we treated this like paper, we could fold it along the x-axis and it would match up. So we have that type of symmetry, and that type of symmetry, again, does not represent a function. Same reasoning here, because this would not pass the vertical line test. If I were to draw a vertical line, it is possible to pass through this function more than once. Therefore, this does not represent a function. So we can have this symmetry here again with respect to the x-axis. And then finally, we can have symmetry with respect to the y-axis. And this is saying that we could fold this across the y-axis and it would match up. Functions with symmetry with respect to that y-axis, those are considered even functions, okay? So the main point here is that odd functions have rotational symmetry about the origin, and even functions are symmetric with respect to the y-axis. And functions displaying symmetry with respect to the x-axis, although that is a type of symmetry, that does not represent a type of function. All right, so now that we visually understand what these different types of symmetry are, let's talk about the algebraic process we would use to determine if a function is even, odd, or neither. And I'm noticing that function there is misspelled. That must have had something to do with the PDF conversion. So algebraic process to determine if a function is even, odd, or neither. Essentially, all you want to do to determine the even or oddness of a function would be to plug in negative x. All right, so we're going to plug in negative x to the function and we're going to simplify. If I plug in negative x and it results in, after I simplify, me being able to factor a negative out in front, and we have negative or opposite that original function, meaning, oh, and I'm noticing all of these are spelled wrong, but we understand that means function. If we're able to pull the negative out in front and we have the opposite of the original function, meaning all of the signs changed, if all of the signs change, we would say it's odd. If we take that same negative x value, we plug it in and simplify, and it returns the exact same function, meaning no signs change. If no signs change at all, then that would represent an even function. And then, of course, if we have the situation where some signs change but not all, then we will say the function is neither even nor odd. Let's look at a few examples. For the first example here, we're given the function f of x equals negative x squared plus 3. So again, as we've just said, all we're going to do is we're going to plug in negative x and we're going to look at how this simplifies. So f of negative x looks like negative, we're plugging in negative x, so that quantity squared, plus 3. Now we need to look at simplifying. So x, when you square it, is going to become x squared. If you square a negative, squaring a negative times a negative, that would represent a positive. So I have negative, and this becomes positive x squared plus 3. So noticing here the square was on the outside. Here I have applied that square. We get x squared, and it became positive because a negative times a negative is a positive. So noticing that negative is still in front. This is negative x squared plus 3. So now I ask you to look. Is this the exact same function we started with, or is it the exact opposite function? Could I factor a negative out and it would be opposite? And of course, you guys can plainly see that it is exactly the same. So I plugged in negative x and I got out the same or original function. And what that means to us is that f of x is even. And of course, if I were to graph this, you could graph it on your graphing calculator, you'd see that you'd get a parabola opening down, centered on the y-axis, and then y-intercept would be up here at 0, 3. So you can see it would fold on that y-axis. And remember, even functions have symmetry with respect to the y-axis. So this function in example 1 is even. For example 2, we're given the function g of x. G of x is equal to 2x minus 3x cubed. Again, we're going to look at our instructions. The first step to determining if something is even or odd is to plug in negative x. So g of negative x, that would look like 2 times negative x minus 3 times negative x cubed. So I've plugged in my negative x. Now I need to simplify. Let's take a second and look at what negative x cubed would look like if I were to multiply that out. So that means negative x times negative x times negative x. You can see there, clearly we would have x cubed, but would this be negative or positive? Negative times a negative is positive, multiplied by another negative, this would remain negative. So as we look at simplifying this, I have 2 times negative x, which would of course just be negative 2x. And then I have minus 3 times negative x cubed. So I have negative 2x, and that would become plus 3x cubed. So now we look at our simplified function here, and we say, well, how does this compare to the original function? And it looks like both of my signs changed. That was positive turned negative, and negative turned positive. So all of the signs changed. Another way we could think about this and trying to make this look more like our definition, I could factor out a negative 1. That leaves me with 2x minus 3x cubed, or in a sense, negative the original function. In this case, that's negative g of x. So I plugged in negative x to my g of x function, and it returned the opposite of g of x. So by definition, if it returns the opposite and all of the signs change, that means we have an odd function. So opposite, we would say that g of x here is odd. Let's look at one more example. For example 3, I have h of x equals 2x to the 4th minus 5x plus 8. Again, we're going to start by plugging in negative x. That's h of negative x equals 2. Negative x to the fourth minus 5 times negative x plus 8. So I have 2. Negative x, if I'm raising it to an even power, those negatives will have a bunch of pairs, so that will cancel out and be positive. So this will be just positive x to the fourth. Here I'm going to have plus 5x, and then I'll have plus 8. So in this situation, if we look at the signs, we have the same. Here we have opposite, and here we have the same signs. So you'll notice that some changed, but not all. This function is neither even nor odd. And that's the general idea between determining if functions are even or odd. When we move forward into trig, we talk a lot about even and odd functions, cosine and sine, and their symmetry. And so we use these properties a lot moving forward in future math classes to help us simplify a problem we may be working on. As always, please feel free to reach out if you have any questions or concerns. Good luck.